Imagine if Gmail loaded. Yeah, there's no explanation.
At least tell me it's a Wednesday.
I don't know.
Oh, yeah.
So, tentatively, this is my plan for the end of the semester. Obviously, I don't have assignments like numbers in yet, but this is kind of like ideally what I'd like to try to get done. I think I would, given what I'm looking at for this most recent test, I'd like to do one more here this semester. I think that'll probably be to all of our advantage, or almost all of our advantages, to do that one more time. This test coming up, well, it was one of those, like, I put you in a position that it was going to be really hard to do well. And that's my fault, right? But we still have to figure out something to do with it. I haven't finished grading them yet. I don't know how I'm going to end up doing, like, I'm still exploring my options as to, like, what's going to be the fairest way to kind of come up with an assessment on this. We'll talk about, like, what that looks like, if that's something that I want to end up thinking that's a good idea or not. Yeah. Yeah.
Oh,
yeah. Yeah. Yes.
Wait, so retake option in there?
Yeah, it's a retake or a double, right? And the retake is capped at 85, but 85 is pretty good, right? I'd be pretty stoked to. I would figure something out. You know, probably similarly graded as the first time around. Yes.
If we go to retake a test, when will we retake the test?
Probably in that sometime between the fourth test and then yeah. If that's something that you're looking to do, I would try to find we'll try to find a time in between those. Does that feel all right? Okay. Yeah, Pierce. Well, I haven't written the midterm for this year. I've rewritten every test that I gave last year. So I don't know if I'm going to rewrite the midterm or not. Probably to some extent, because I think I'd like to do some multiple choice, and I didn't do any last year.
Yeah, but like, didn't you say that like the curving scale?
Look, I've curved everything you guys have gotten so far. So I will when it comes time for me to write the final exam, I will let you know when I know the format that I'm going to give. But I'm still kind of like just trying to get through grading test 3 and want to get to test 4 before I can start doing a good job of writing that. And I have to be really careful about the length, because this most recent one, I certainly got us into some trouble by not paying enough attention to how long this was running. Carmen.
So I'm not going to be here on the December 1st. That's our last day of Kairos.
Okay.
So could I have to take the test on the 5th?
Yeah, of course. Yeah, we'll figure it out. Or if it has to be later than that, it can be later than that. Yeah. Okay. Yes, Elaine.
So hypothetically, if we were to retake the test and do worse than we expected,
You get the new worst grade. Yes.
Really?
well, I'm not doing it. You don't get the better.
No.
when you started.
Yeah. Okay, Braden.
So when you say double the highest test, you're just putting.
You'd get a 5th test score of whatever your highest one is. So usually that's the safer option. And unless you have like, I got like A's and B's on 3 of them and then I got like a 46 or something on then that's a case where like, doing the retake makes a lot of sense for you. Or if it's just like the end of the semester just looks like chaotic mess and it's like, I don't want to cram another test day in, I'll just take the double. Totally fine. Like, that's safe because you're guaranteed that it makes your score better. Okay, so let's
Would this test be up for a possibility of doubling?
the fourth one?
Yeah.
Of course. Of course.
I'm thinking, and does multiple choice practice fall into open homework?
Sure. Sure.
I'm writing down every single one.
I'm gonna cry.
So that being said, your homework has to be on physical sheets of paper because you're not going to be able to, I'm not going to let you use a tablet. So either if you're a write it in OneNote person, make sure that you've printed these out and that you've written it in a way that like it'll print onto a page nicely for you. Or if you're a by hand person, that like you have that stuff organized and you're ready to use it. I would caution you though about like, well, yes, make sure you still study, but other caution is don't come in with like this thick of like a stack this thick, because that's too much. You're gonna spend all your time leafing through that for what you need, right? Like don't feel like I'm gonna try to get everything. Just be like, you know what? Like I'm gonna take the stuff that's hard, and I'm gonna make sure that that's where I need it to be, and the stuff that I feel good about, I'm probably just gonna study and be good with, and I'm just kind of using the open homework as like some backup if I run into a particularly difficult like related rates problem, or if I need a example on using like L'Hopital in maybe some of these more difficult situations. We haven't talked about what that is yet, but we will. But you know, like that's really the way I would think about it. I know it's tempting to be like, I'm gonna have like 100 pages of, you know, like, okay, I don't know how useful that's gonna be to you because you're gonna spend a lot of time looking through things. Time will be an issue because you still have to like be able to go. But yeah, it'll be open homework to look at.
Are you still gonna do the like test breakdown thing when having homework problems?
Yeah, I didn't want to do this yet for 3-9 or do the homework quiz for 3-9 because I just felt like everyone was going to come back and feel terrible about what they've done for the homework. And we're just going to need some time. So I'd like to do like a half an hour today of 3-9 questions. And then I would like to start 4-1 and maybe do another half an hour of 3-9 again, maybe another day, and kind of just kind of go on this. And to be honest with you, with a open homework test coming, I don't know that I even really need to do a homework quiz on these homework problems in between, because you're insane not to do them, right? So I know you're going to do them because they're going to be eligible for open homework. So like, what do I need to do a homework quiz for, right? And that buys me a little bit more class time, which I'm cool with. Does that feel okay to everybody?
Yes. And
All right.
we dropped the lowest homework quiz, right?
I think 2 probably. We've done so many. We're probably up to like 12 or 15 of these things already.
Do we have to drop one?
Well, that's only going to it cannot make a grade worse
I
if they're
know,
dropped.
I feel like the more points in the grade do.
They're different categories. Yeah, so it cannot make your grade worse by dropping. Promise.
It's like drop a quiz in a homework
Yeah.
grade. Can we like, instead of dropping the quiz, can we drop another homework grade? Like,
Oh man.
I know you're behind.
whatever.
Okay.
It's okay.
All right. Shall we begin?
I think that would help quite a bit.
Yeah, that would be massive help. Who am I missing? Am I missing anyone? Is there anybody absent? I didn't even like look at my seating chart here. I think we're all here. All right. All right.
Yeah, double the highest test and then drop your lowest. It's always been like that.
All right. So let's look at some of these 3-9 homework problems. I'm going to start with the book stuff. Okay. In the future, we'll look at some of my AP classroom problems. I will get that a PDF in there. I forgot to do that. I told you I was going to do that, didn't I? And I forgot. I'm sorry. Nobody emailed me about it, so I don't think anybody could have been that mad. Yeah. Okay. Rita.
Number 24.
You want to start with 24?
Yeah.
Okay. Okay, and that's awesome because that's one of the ones that the PDF that I made for you guys, or the book PDF I have, for whatever reason, that particular page is like corrupted and it won't open. So I took a picture of it and put the picture in for that one page. Okay. A trough is 10 feet long and its ends have the shape of isosceles triangles that are 3 feet across at the top and have a height of 1 foot. If the trough is being filled with water at 12 cubic feet per minute, how fast is the water level rising when the water is 6 inches deep? Okay. Where did my pen go? There you are. So let's start by drawing ourselves a picture, right? So we have like some trough. Right? How's that for some art skills? Did I do okay on that? So 10 feet long. And these guys are 3 feet across. And I think we are 1 foot high. And then we're filling at 12 cubic feet per minute. And then it says, how fast is the water level rising when the water is 6 inches deep? So far, so good with our setup here. Okay. So what formula are we going to use that describes what's going on here? Volume of this trough, right? Who remembers the formula for a prism, like a rectangular prism? It's just area of the base times the height, right? AP geometry would be rough.
Yeah, I do geometry.
Huh? No, it's not an AP class. I'm just saying if they made it an AP class, it'd be rough.
Yeah, I know.
Kind of a breeze.
Yeah. No, I'm just saying that, like, okay. And what is the and I'm going to put height of the, I'm going to put a subscript P on that, where the P is for prism, because we're also going to have heights for the triangle, which is the shape for our base. I don't want to get confused about which one we're talking about, right? Okay, so what is the area formula for a triangle? Okay. Everybody feeling okay to hear?
Yeah.
Are any of these constants?
Yes.
Yes.
Air,
10 feet.
base, the triangle, height of the triangle.
That is the only constant. Because as the water is filling, the rectangular prism formed by the water in the tank, the length of the water never changes, right? But the height of it and the base of the top of the triangle formed by the water would be changing, right? So yes, we can change that to a 10. So far, so good? Now, if I try to differentiate right now, what's going to happen?
You're gonna have too many.
I would have two differentials, right? I'd have dB dt and dH dt. dH dt is fine because that's what I'm looking for, right? But I have to do a product property, so I'm going to get a differential from each of those two variables. So what I'm going to want to do here is I'm going to want to find a way to rewrite the base of the triangle in terms of height of the triangle. Mm-hmm. Is everybody okay with what we've drawn so far? There's one other important additional information that was written in the question that we haven't used yet. Isosceles triangle, very good. Right? I guess I should do that. So what can we say about sure, the two triangles are similar. So you could say like 3/1 is equal to the base of the water over the height of the water, right? Or that the base of the water is 3 height of the water. That sounds good to me. Everybody okay? So I've changed this to waters from tanks, right? Because I know that the volume of the tank formula is going to be the same as the volume of the water formula, right? Because the water is just a smaller tank, but with the same proportions. All right. So now I think we can differentiate. Oops. The derivative of HW squared. Right? Like if I did the derivative with respect to x of y squared, I get 2y dy dx.
Yeah, but the outcome, like, you did.
Oh, I shouldn't have said
Yeah.
it should be 15. That's what you're arguing about?
Yeah.
Yes. Yeah, yes. Thank you. So far, so good. Now, if we fill in, we know the volume is changing at 12. The height of the water is 0.5, 6 inches, so that's half a foot. And if I reduce that down, what's that going to be? 4/5. Let's go take a look in the old answer book and see if that's what we're supposed to get. You guys wouldn't know because this is an even. But I think that ought to do her. I did all these at one point before assigning them, but it's been like a couple of years. Oh, good. It always feels good when you can do it without having looked at what you're supposed to get beforehand. Great. Yeah. So were you good with how we drew this picture? Okay. And were you good with how I came up with this proportion? Sure. I said for the big triangle, base over height should equal the base over height for the little triangle. Since they're similar figures, their side length should be proportional. And then I just got the BW by itself. So I like cross multiplied or whatever. Does that feel okay? Okay. So I did like, said that. Now you could have written that as like 3 over BW equals 1 over HW. Yes, you could have written it that way. You know, or like as long as the proportional pieces always, or corresponding pieces line up either up and down or left and right, it's fine. The proportional work out to be the same thing. Does that feel okay? Okay. Isabel.
BT and
So the base of the tank is the 3. Base of the water is like the little triangle formed by the water. So the base of the tank is a constant. It's 3. But the water makes the same shape as the shape of the tank. It's just its dimensions are different. So BW is like the base of the triangle where the water is.
So because the same shape, is that why the BW that equation is the same thing as the BT, but just
A different numbers potentially in it. Yes. Yes, 100%. Right? Like if I fill up like a cylinder has a volume formula. If I pour water into it, the water is also going to be in the shape of the cylinder, but its dimensions are going to be different. But it's going to be the same volume formula to calculate it. It's just the numbers you're plugging in would be different because the shape is different, or the dimensions are different. Right? But it's still the same formula. Does that feel okay there? Was that appropriately speeded that we walked through that? I tried not to go very fast so that we didn't lose anybody and we talked through it pretty thoroughly. Should we do one more? Elena. 12. Sure. Are you talking about from the problem? 12 is just like a question. There's no part. Oh, I see. Yeah, never mind. I see it. Yeah. Okay. It's like that just I didn't see that part. And then there's that. Okay. All right. All right. If a snowball melts so that the surface area decreases at a rate of 1 square centimeter per minute, find the rate at which the diameter decreases when the diameter is 10 centimeters. So, like there's our snowball, right? We're told dSA dt is going to be 1 centimeter squared per minute. Now, I've written something wrong here intentionally. Yes, why is it negative? Yes, good. And then we're asked to find this is dumb, dd dt. And we should say when the diameter is 10. Everybody's okay with that? Okay. So that's our quantities are given, right? That's the unknown. We drew a picture. Write the equation that relates the quantity. Who remembers the surface area equation for a sphere? Go. Yes. So yeah, this is the change in diameter with respect to time when the diameter is 10 centimeters. So that's telling us what value of d I'm going to be plugging into the derivative after I figure out what the equation is for it. So that derivative should be in terms of d only because that's the only quantity I know to plug into it. Does that feel okay? Okay. You're good? Okay. Surface area formula. I think 4/3 pi r cubed is the volume formula. I think 4 pi r squared is the surface area formula, but we want this in terms of diameter rather than radius, right? So I would think about it this way, right? Because 2 radius is a diameter. Well, because the 4 is 2 times 2, right? So I took 1 2 and put it with 1 r and took the other 2 and put it with the other r, which is what Rita said, but I didn't want to jump right to it because nobody's familiar with that formula for surface area. I had to think about it for a second when you said it. I'm like, we're going to do it the long way so that everybody's okay with where that came from. But if you looked up surface area for a sphere, I'm sure it said 4 pi r squared and not pi d squared. No, it's fine. You're good. It's correct. Everybody's good with where I've got to here? Now, if I look at this equation, what I'm excited about is it's only in terms of diameters, which is great for me because my derivative I want is in terms of diameter, right? So I'll just do the derivative of both sides now. So dSA dt equals pi times 2d and then d dt. Everybody's good with that? So let's plug some stuff in. So I can plug in the derivative for surface area. I can plug in the value for the derivative or the the diameter now, because now that I've differentiated, that's when I want to figure out the rate, is when the diameter is 10. So until I have a rate function for the diameter, I don't want to plug the 10 in. I have to do it after I've done the derivative, so I have the ddt, dt.
So stop the equation.
Right here?
And, yeah, so that's
Yeah,
the equation
that'd be
that
fine.
we're solving.
Yep. And this would be whatever we're in. What are the units here? Is this like feet per minute or something? No, centimeters, huh?
Yeah.
Does that feel okay there, Elena?
Yes.
And these ones here that we're doing where there's requires no substitution, right? It's just like a single equation to set this up. This should feel comfortable. Like if you can get the picture drawn in the equation, the calculus from here should feel comfortable. There's not any tricky algebra going on. There's not any weird, like what's a constant, what's not. This kind of a problem should feel pretty comfortable right now. The first one, the one that we did to start that Rita had asked to do, would be on the verge of this is starting to get hard because you have to do that change of variable piece. That's tricky. Now that particular one was a pretty easy change in variable to do because everything you needed was like right there for you, but you still had to recognize that you needed to do that, which is not trivial the first few times through. Okay, let's do one more and then we're going to move on to 4-1. Deal? Okay. Who wants to pick? Isabel. 48? 28. I was like, was there 48 problems? It ended at 46 in case we were curious. All right, 28 says, a kite 100 feet above the ground moves horizontally at a speed of 8 feet per second. At what rate is the angle between the string and the horizontal decreasing when 200 feet of string has been let out? Okay, so I'm going to try to draw this so I'm kind of embedded on the XY axis. I'm going to label this side as X, this side as Y. I'm going to call that side S for string because that's where the string is. I know dx dt is 8 feet per second. And we're looking at d theta dt when s equals 200. Oh, and I'm sorry, we're told y is 100, right? Okay, so I would almost think about this as a second piece down there, right? All right. Let me just, kite 100 feet above ground moves horizontally at the speed. What rate is that? You know what? I think that reads to me as constant. Right? Yeah. Okay. So, I want to come up with an equation that relates or describes this situation. I know that equation must include theta, because we're looking for d theta dt, and it must include x, because I'm given dx dt. Rita? Well, I would also probably want this, because if I differentiate that with the s, I don't know ds dt. I would use tangent or cotangent, because I know about adjacent, or I have information about adjacent, and opposite is constant. So I would probably either pick tan theta equals y over x, or cotangent theta equals x over y. But y is a constant, right? Which one of those two looks more appealing to deal with? You are a bunch of liars.
Oh,
Why would cotangent be the better one to deal with?
1 over x or 1 over 1.
Oh,
Yeah, there's just, the derivative is super duper easy, right? The derivative of that is just 1 over 100. That's why I would pick that one. That's okay. What's the derivative of cotangent? Yeah, I think it's negative cosecant squared. Is that right? Yeah, why is the theta, d theta dt equals 1 over 100 dx dt. So far, so good? Okay. So this is going to be, to move the negative cosecant squared to the other side, I could divide by negative cosecant squared, but really what's that the same as? Multiplying by negative sine squared, right? Because sine and cosecant are reciprocals. So dividing by cosecant is like multiplying by its reciprocal. And I'm going to write it this way, because I'm about to start filling some stuff in. Okay. We know what dx dt is, right? That's 8. What is negative of sine theta? No. I'm just going to go to the picture. Sine is opposite over hypotenuse, right? 100 over 200. Is everybody okay with that? We were wondering where the 200 was going to come in, right? Now, the other option there you could have had would be to use the 100 and 200 to figure out the angle for theta, and then plug the angle for theta in there. But like, I'm just going to use the triangle, because probably this would be a no calculator problem given the numbers involved. And good luck doing sine inverse without a calculator. So 100 divided by 200 is 1/2 and squared is 1/4. So that gives me 1/50. And this would be radians per minute or something? Per second? Per second. I lost the negative sign somewhere, right? Oh, yeah. Look, I'm dumb. Sorry, hold on. This negative right here isn't inside the squared, right? So I'm just going to stick that out front. Just right, so there we go. It's like, that's not right. It should be getting smaller. If it's being pulled horizontally, like my angle should be getting smaller, right? Sorry about that. Isabel.
Could you just explain like the 100 over 200?
I went to this triangle. Sine is opposite over hypotenuse, right? So opposite over hypotenuse.
They told us that as
It did in the problem. Yep, and that was one of those things I was wondering where we were going to use that. It's like, hey, I haven't used it yet. Starting to get a little suspicious here, but there it came in right at the end. And this one, although the setup was a little unfamiliar, you didn't have to do any change of variable. There's no like replacing a variable, like having to find a second equation. It was once you had it set up and your picture drawn and you chose the correct equation, as long as you picked tan theta or cotangent theta, should have been okay. The tricky part was, like, should I pick sine? Should I pick cosine? Should I pick secant or cosecant or tangent or cotangent? That would have been the hard part, was deciding which of them you wanted to use. Okay, I'm going to stop here for today on 3.9 stuff, and we're going to talk about 4.1. Okay? Sure. We're going to continue making some time during the week to do more 4.1 stuff, or I'm sorry, 3.9 stuff. Today, or really throughout most of chapter 4, we're going to be looking at applications for derivatives. So like the relationship between a derivative and a function. So we're going to start by just kind of remembering a couple of definitions from algebra and pre-calculus. So we're going to start with an absolute maximum. It says the absolute maximum of f on its domain D is if there's some f of c that's greater than or equal to f of x for all x in the domain. What is that really just saying? It's the biggest y value, right? Or tied for first biggest y value, right? F of c is just some specific y coordinate. And it's the biggest or tied for first amongst all the y coordinates in our function. Yes. Sure. And then the absolute minimum is the same idea, except instead of the biggest y coordinate, it's the smallest. Now, we also should remember from algebra 2 and pre-calculus that we also can have local maxes and mins, right? A local max is the highest point in some neighborhood surrounding x, right? So like if I look at a little area, it's the highest or lowest point in the area, right? Maybe not, maybe there's some bigger ones or smaller ones way out away from it, but if I look at just like, hey, what's going on around this value, It's like the biggest or smallest point in that neighborhood. Everybody's okay with that? So like, let's take a look at this guy here. So that's the function f of x equals 3x to the fourth minus 16x cubed plus 18x squared. And we've just graphed that on the interval from -1 to +4. So if we look at this, come on, you stupid thing. What do we see as the maximum or the absolute maximum, absolute minimum, and then local max or mins here? What do we see?
Absolutely 37.
So the absolute maximum, where did my pen go? There you are. Yeah. Sure. And then what's the absolute minimum?
3 negative 27.
And the others are,
5.
right? Local min, local max. Is this something? Yeah. Hold on a second. Okay. So here was the question, and I answered it incorrectly. So this 4 comma whatever, this point here that we called a local maximum, yes, of course, yes, is not local. And here's the catch. When we say near C, that's near is implying an open interval. Here, if it's in the domain for our question, that's implying a closed interval. So you can have absolute maxes and absolute minimums at the endpoints, but you can't have a local max or min at an endpoint. Everybody okay with that? Because near implies an open interval. So there's no thing in the domain that I can give an open interval and include 4 in, right? You guys agree? So if this was to, if it went to 5, it would keep going, right? So it could be like a local if it did like that and kept going. But still, again, at the end point, you can't have a minimum or a local anything. Okay, so note that, come on, you stupid OneNote. Note that this one cannot be called a local max, but this one could also be considered a local minimum, right? It's not an endpoint. Everybody's okay with that? All right. Important idea. This one gets a name. Do you think this is one worth memorizing? Should go right down with like squeeze theorem and intermediate value theorem. This is an important one. This is the extreme value theorem. And it says if f is a continuous function on a closed interval a, b, then f contains an absolute maximum f of c and an absolute minimum value f of d for some numbers c and d in the closed interval from a to b. Notice it says absolute maximum, absolute minimum. Why doesn't it say local there? It's because of the closed interval, exactly right. What if we had this? This can still be our absolute minimum, this can still be our absolute maximum, but they can't be locals, right? So if we tried to say this for locals, that's not true. Everybody's okay? That's another one we should be able to quote verbatim, just like the intermediate value theorem and the squeeze theorem, where you will use this to answer questions on the AP exam. Like there very likely will be a question, does f of x reach a absolute maximum or minimum on this interval? And then you have to justify your answer. And this would be, quoting this would be your justification, right? You have to show that f is continuous. And then would be able to quote that from there on. So here are some examples of just kind of showing how this is working. Right, so this is our f of c, that's our f of d, our absolute maximum minimum, right? Everybody can see that? Here, there's our absolute maximum. Here is our absolute minimum. Notice that that could not also be local minimum because it's at an endpoint. Here we have two absolute maximum. That's okay. They're tied for first. They can both be absolute maxes. How many absolute maxes could you have? Infinitely many, right? Well, think about the graph for cosine. How many absolute maxima does cosine have? Infinitely many, right? Its domain is all real numbers. It goes on forever. How many times does it hit positive 1? Too many times to count, infinitely many, right? And then we have one local minima. Could we have more than one local minima, though? Or absolute minima?
Yeah.
Yes, right? How many could we have? Infinitely many, right? Cosines are still our same example of that. What these next two are showing you is why we need continuity. Notice in the extreme value theorem it says if f is continuous from A to B. Let's look at an example here where we lack continuity. So if we look here from 1 to 2, do we have a absolute maximum? Look real close. It's open. I know it was hard to see. That's why I zoomed in so much. So no absolute maximum. Is there an absolute minimum? Yeah, right? So you could lose one of them if you don't have continuity. Let's look at this next example, though. Is there an absolute minimum? No, right? Open circle. Is there an absolute maximum? No, because it's going on forever, right? It's infinite. So you could actually have neither. Oh, okay. So continuity is critical, right? If we don't have continuity, we can't expect to be finding an extreme point, an absolute min or max. We still might be able to find it. They still might exist, but they don't have to. Next idea. This is called Fermat's theorem. It's French, so you don't pronounce the T at the end. It says if f has a local maximum or minimum at C, then the derivative of C exists and f prime of C is equal to 0. Yes. So if we have a local minimum at C, or a local extrema at C, and the derivative exists, then we know the derivative at C is equal to 0, right? I think I might have missaid that the first time. GG. So, yes.
Sorry, you just said if we have a local extrema at C and the derivative exists, then we know that the derivative of C.
Yeah. So here's the caution though. The converse is not true. Just because the derivative is 0 doesn't necessarily mean you're going to have a local minimum or maximum. Think about what the graph of x cubed looks like. The slope at that point would be 0. Is that a local min or max? No. How about the absolute value function? Is this a local, or is this a local min or max? Yes. What's the derivative there, though? Doesn't exist, right? So we have to be careful about this, right? Just because the derivative is 0 doesn't guarantee that it's a local min or max. And just because I have a local min or max doesn't mean the derivative there is 0. Okay? We have to have both, right? I have to have the local min or max and the derivative existing to guarantee the derivative is 0. And the converse just is not true. If your derivative is 0 does not mean that you have a min or a max. Everybody's cool? Okay. Notice that this is a pretty conceptual section so far, right? We haven't done really a whole lot of calculus. This is just idea building, but they're not complicated ideas, right? All right. So what we're building towards is trying to figure out where these extrema are. So the next thing we're going to do is define something called a critical number. We say a critical number of a function is a number C in the domain of f such that either the derivative of f is 0 at that C or the derivative is undefined at that C. So there we're accounting for our absolute value of x problem, right? What do you think we're going to do with these critical numbers? These are our candidates for our extrema, our local maxes and mins, right? So eventually we're going to start putting this all together and start being able to algebraically find the locations of our extrema. Remember in Algebra 2 and pre-calculus where we always just used the calculator to find the max and min? And we said that there's not a good, you don't have an algebraic method to do this yet. That's what's just happening. We're heading towards eliminating that yet. But here's the lovely part, is that as you're doing your assignments, guess what you're going to be able to do on your calculator? Check them. Because you know how to find local maxes, or find maxes and mins on your calculator. That's something we've done a bunch of times. All right. So let's start by, or let's do this example next. So it says to find the critical numbers for f of x equals x to the 3/5 times the quantity 4 minus x. So before I do anything, I'm going to sit here and take a moment and think about what is the domain of this function. Because that's important, because I need that number c to be in the domain of f. So I need to know what the domain of f is. Who can look at this and tell me what the domain of f is? Rita. It would not. Carmen, did you have an idea?
Would it be the x
Nope.
Negative 0.
Nope.
All the numbers.
All real numbers is correct because this is just a odd root. I have something to the 1/5 power. That's an odd root. I can take the odd root of all real numbers. This is just a polynomial whose domain is always all real numbers. So I would expect the domain to be all real numbers if I have the product of two things whose domains are all real numbers. Is that okay? All right. So let's find the derivative of f of x now. What's going to be the easiest way to do that? Oh, no.
Chain rule.
No. What? What do you mean power? But you have two things multiplied together. No, don't do that either. Distribute it.
That counts as differentiating?
No, but it's going to make doing the derivative way easier because what do we get to avoid when doing that? Yeah, the product rule. Is everybody okay how I got the 8/5? 1 plus 3/5 when I multiplied the things? Okay, now what's the derivative? Good. Everybody's good? Okay. And now what do we need to do? Critical values. Let's look at this thing first as a whole. What's the domain of this? It is still, not quite.
Oh, because we have the negative.
Can't be 0.
Yeah, right? The issue is that we have an x to a negative power, so we know that can't be 0, right?
Yes.
So our one critical number is certainly 0, since the derivative doesn't exist at 0, but 0 is in the domain of f. Is everybody okay with how we did that? How? Oh, that shouldn't be inverse. That should just be f prime, sorry. Pierce, because I thought about this as 12 over 5 x to the 2/5. And if I have 5 in the, or 0 for x, I have a 0 in the denominator. That's it.
All right.
Cool? All right. So that's one. What is the other possibility for a critical number? When the derivative is equal to 0. So how are we going to solve, let's write it this way. How am I going to solve this equation equal to 0? No. Get real, you boogers. Well, let's think about it this way. Guess and check. So let's multiply both sides by 5 right away, right? Get rid of the fraction. So far, so good. Okay. And what I'm going to do now is I'm going to factor out a greatest common factor. Well, let's divide the 3 or 4 out of there. So no, we don't have to worry about that also. Oops. What is our greatest common factor between 3x to the negative 2/5 and 2x to the positive 3/5? I would take out an x to the negative 2/5. When I divide x to the positive 3/5 by x to the negative 3/5, what do I get? X to the first, right? That's correct. So I did x to the 3/5, and I'm factoring out, so I'm dividing x to the negative 2/5. So I'm subtracting the denominator. So I have 3/5 minus a negative 2/5, which is just 1. So I can now apply the zero product property. Well, I know that if I have an x and like 1 over x to this whatever is never equal to 0, right? Like 1 over x has no solution. And I take the other one. So those should be my critical numbers. Feel okay? All right. So with that, we're going to come with statement 7 here. It says, if f has a local maximum or minimum at C, then C is a critical number of f. So if we're searching for local max and mins, all we need to look at are the critical numbers. Everybody feel good there? Now, what happens if instead of looking for only local mins and maxes, what if we want to look for absolutes as well? So here we're going to come to the closed interval, what we'll call the closed interval method. So to find the absolute maximum minimum values of a continuous function f on the closed interval from a to b, we find the values of f at the critical numbers of f on the open interval from a to b. Then we find the values of f at the endpoints of the interval. And then we take the largest values from steps 1 and 2, that's the absolute maximum, and the smallest is the absolute minimum. So we're going to find the critical numbers, plug those values back into f, take the endpoints of my interval, plug those values back into f. From that collection of numbers that we have, the biggest number is the absolute maximum, smallest number, absolute minimum. Dunzos. Let's do an example. Sound good? So the calculus here and the algebra are pretty light. It's not so bad. Let me just look. Okay, so we just have some examples after this. Good. All right. So first thing I'm going to do, what's the domain of f? Well, no, it's given to us, right? Yes, it's a polynomial, so it's all real numbers, but here the domain is less than that, okay? What's the derivative going to be? Okay. What's the domain of that going to be? Good, so it's still going to be the same as f, right? Why did you know it was all real numbers? Still a polynomial. Excellent. Everybody good? We love polynomials and exponentials. They're all real numbers also. Every time, which is lovely.
What does that look
Like e to the x.
Oh, yes.
Okay, so our critical numbers now will not include any things that are undefined. So all I have to do is worry about setting equal to 0. To solve this, what do I need to do? Excellent. And then I set these each equal to 0. And I get critical numbers of 0 and 2. So I'm going to do f of 0, which is 1. F of 2, which is 8 minus 12, that's -4, plus 1 more is -3. And then I also have to do f of the endpoints. So f of -1/2, let's see, that's -1/8, and that's -3/4 plus 1. I don't care what that is. It's bigger than -3 and it's less than -1. So, it's something. What is it? It's 1/8. Right? -3/4 plus 1 is a quarter. A quarter minus an eighth is an eighth. Right? Sounds right. If I do 4, what is that? That's got to be our maximum, right? I got 64 minus 48 plus 1. So 65 minus 48 is 17. Okay, so what are we going to say? Our absolute maximum is the point 4, 17. And our absolute minimum is 2, -3. How's that feel? Really good, right?
Amazing.
Yeah, this is okay. All right. We'll do one more example here because I think we can do this next one without worrying about it. I'm going to skip part A because we all know how to do this on our calculator, right? So part B. So our domain for f, well, that's just given to us. Well, we're doing the closed interval method, so yes, if they didn't, if it was over the entire domain, then you'd really have to be careful and think about it. All right, let's find f prime now. What's that going to be? Yep, 1 minus 2 cosine x. What's the domain for that? Excellent. How do you know that? Because it's sine or cosine. Not all trig functions are all real numbers. Tangent, cotangent, secant, cosecant have asymptotes. But sine, cosine we love. Those are just all real numbers. Okay. So then we take our derivative and set it equal to 0. So cosine x should be 1/2. So x should be cosine inverse of 1/2 on the interval from 0 to 2 pi. All right, my trig experts, who remembers the values or the places on the unit circle where cosine is equal to positive 1/2? No, 60 degrees, pi over 3, and, well, let's say 5 pi over 3. First and fourth quadrant is where cosine is positive, right? Because x is positive. So 60 degrees up, 60 degrees down, because you want the x to be the shorter, right? X is long at 30, x is short at 60. Everybody's okay with that? That's just how I picture it in my head. I don't memorize them, I just picture it in my head. I know there's only 3 options that I'm responsible other than the quadrantals, 0 and 1, where you're landing on an axis. Don't let her punch you in the back of the head like that. All right, so these are our critical numbers. So f of pi over 3. So that's going to be pi over 3 minus 2 times sine of pi over 3. What's sine of pi over 3 if cosine is 1/2 at pi over 3? Root 3 over 2. I heard somebody whisper. Say it loud so people can look at you and go, yeah, look at that smart cookie. Okay. And then we'll do f of 5 pi over 3. So 5 pi over 3 minus 2 times sine of 5 pi over 3. What's sine of 5 pi over 3? Let's go triggers. Somebody whispered it. Somebody say it loud.
What was the question?
Sine of 5 pi over 3. Negative root 3 over 2. Yeah, you're in the 4th quadrant. Y is negative.
Yeah. It's just the opposite.
Okay, and then we have to do f of 0. What is sine of 0?
0.
0. And sine of 2 pi is? Let's go, sine of 2 pi. 0. Okay, so what's our absolute max? Yeah, 5 pi over 3 plus root 3. How are you sure that that's more than 2 pi? I think it's real close, but I think you're right. 2 pi is like 6.2, right? Square root of 3 is like 169. And 1/3 of a pi is going to be like a little bit more than 1. So I'm pretty positive that's bigger. But let's check real quick. Yep. Okay, what's our min? Yeah, it's that one, right? You could if you had a calculator.
Oh.
This is a perfectly reasonable no calculator question. It would be it's a little tricky, but I had to think for a minute, but here's what I thought. 1/3 of a pi is just about 1. Square root of 3 is a lot bigger than 1. It's like 1.6 or something. So that's all I needed, like as an approximation. This is that's the homework set. Here's the good news. Most of these are pretty quick, right? When we did these.
Yeah.
Some of them are. Some of them are like just problems like we just did. No, remember we said that if we're going to do a open homework test, I don't think I need to do any more homework quizzes on this stuff because like you're a fool not to do it, right? So, and that gives us more class time to make sure we get all this stuff done.
Have a great day.
You too. Take care.